Continuing on with section 3.3. Okay, next result deals with ranks of products of a certain type, and says, Theorem 3.3.11, if A is a square full rank matrix, so it's non-singular, and B and C are conformable matrices for multiplications AB and CA, then the rank of AB equals the rank of B, and the rank of CA equals the rank of C. So you might interpret it as if we take a matrix B, multiply it on the left by a full rank matrix, that doesn't change the rank. If we take a matrix C and multiply it on the right by a full rank matrix, that doesn't change the rank. So that's one interpretation of what it says. Let's go through a proof. Okay. We know by Theorem 3.3.5 that the rank of a product is less than or equal to the minimum of the rank. We can always choose one or the other. That in turn is less than or equal to the rank of B. If B is the smaller of the two, we get the equality. If A is the smaller of the two, we might get the inequality. So anyhow, we can always say rank of AB is less than or equal to rank of one or the other. Let's choose rank of B. For these computations, given what we're trying to show here, we want to reverse that inequality. We can write B as A inverse AB, right? A is a full rank matrix, so it has an inverse, so that makes sense. And we can then apply this same result and say the rank of B, which can be written as the rank of the product of these matrices, is less than or equal to the minimum of the rank of, pick some of them. Say pick the first one and the product of the second two, treating it as a product then ultimately of two matrices. And we know that's less than or equal to the rank of either of them. We choose the rank of AB. And we've shown then first that the rank of AB is less than or equal to the rank of B. Here we've shown the rank of B is less than or equal to the rank of AB. There's the equality. And then similarly, when we multiply on the other side, the rank of CA is less than or equal to the rank of C. Similar argument. Let's write C as C times A inverse, and then a similar type manipulation up here will give us the rank of C is less than or equal to the rank of CA. And again, we've got the inequality established in two directions, leading us to an equality. Okay, we'll use that in the future proofs a good bit. The constraints were we're multiplying a given matrix on one side or the other by a full rank matrix, an invertible matrix ultimately. Let's see, we can weaken the hypotheses there a little bit. So here A was a square matrix, was a full rank. We could talk about A inverse. The following result is a generalization of that, in which we're taking A to be a full column rank matrix and B a matrix conformable for the multiplication AB. So the hypotheses have weakened from full rank to simply full column rank down here. And then the conclusion is the same. Rank of AB equals the rank of B. Alternatively, if A is a full row rank matrix, and C is conformable for the multiplication to discuss C times A, then the rank of C times A is the rank of C. So similar to the previous one, the requirements on this one are full column rank when multiplying on the left, full row rank when multiplying on the right. Okay. Take A to be an n by m matrix. Okay, I need to give it some dimensions. We're going to say it's a full column rank. Say that rank is m because it has m columns. That would require m to be less than or equal to n. Otherwise, there ain't enough room for enough pivots in the matrix. you think of rank in terms of pivots. But that institutes a dimensional constraint that m is less than or equal to n if we have full column rank. Theorem 3.3.8 guaranteed us that a full column rank matrix has a left inverse, analogous result for right inverses and full row rank, but more of that later. So A has a left inverse. Let's denote it A sub L inverse. And A sub L inverse times matrix A equals the identity matrix of the appropriate dimensions. Those dimensions in this case would be the second dimension of matrix A. So be the M by M identity matrix. All right, theorem 3.3.5, I promised you we get some mileage out of that. Tells us that the rank of AB is less than or equal to the rank of B. So let's take matrix B, write it as I sub M times B. Matrix B must be M times something. After all, it was conformable for the matrix multiplication A times B. Matrix A is N by M. Matrix B must be M by something. That's the conformable condition. Might gloss over dimensions here when we do more of this because we're going to do a lot of it. But the appropriate identity matrix to multiply by is I sub M. And let's see, we have we could write the I sub M matrix, here it is, as A sub L inverse times A. So let's replace that identity matrix with the A sub L inverse times A. Then we've got B written as a product, so we know the rank of B is less than or equal to the minimum of the rank of two matrices which multiply together to give matrix B. Let's choose the matrices A sub L inverse and the matrix AB. So we'll take the minimum of those two, giving us the rank of B is less than or equal to the rank of AB. We just had the rank of AB is less than or equal to the rank of B. So we get the equality. So the proof's not that different from what we had upstairs. Upstairs, we could talk about just straight up inverses. Here, we can only talk about one-sided inverses because we don't have a full rank matrix. We have, say, a full column rank matrix. All right, so let's see. If A is N by M of full, an error here, should read full row rank. We're doing the second part. Excuse me, this should read full row rank, typo there. N, requiring us to have at least as many columns as rows to get that, full row rank in there. And it's a similar type argument. Full row rank gives us a right inverse. We can use the theorem 3.3.5 to draw a conclusion of another type of less than or equal to rank of CA is less than or equal to the rank of C. Same type of substitution we did up here to reverse that inequality and draw a conclusion of equality. Sorry for the typos, but the argument's quite similar to what we have here, except we're talking rows and right inverses in this case. So proof of that one, not so different from the proof of the previous one. Okay, let's recall how we define positive definite matrix. N by N matrix A, which was symmetric, was said to be positive definite if for every non-zero vector x from Rn, x is non-zero, we have the quadratic form x transpose Ax is positive. So that was a definition of positive definite. We're going to talk about positive definite now. The next result shows that positive definiteness is preserved under a particular type of multiplication by a full rank matrix. Okay, we just saw some preservations of rank, in a sense, by some multiplication by, in a sense, full rank matrices. So the statement is, take C to be an N by N positive definite matrix, and let A be an N by M matrix. If C is positive definite and A is a full column rank, then A transpose CA is positive definite. This is the converse. If A transpose CA is positive definite, then A is a full column rank. Given the dimensions of A, the column rank will be M, and M will have to be less than or equal to N to get that full column rank. Okay, so we'll go through proof of that. Now that's going to require this type of condition here. So this is what positive definite means. So we're making a claim in part 1 of positive definite. Okay, let's go through part 1. So we need to take ourselves a matrix of appropriate dimensions, vector appropriate dimensions, X and Rm, non-zero, and let Y be A times X. Okay, so we're going to make that substitution. You'll see why shortly. So by defining Y as this type of product, you know whenever you take a matrix A, multiply on the left by a vector, you get a linear combination of the columns of A with the components of vector X as the coefficients. So what we're saying is Y is some linear combination of the columns of matrix A. Since A is a full column rank, that means the columns are linearly independent, which is an implication that if X ain't 0, if you're not taking a vector of all zeros, and we're not, then we've got a linear combination of the columns where not all the coefficients are 0. Okay, linearly independent set, that's not going to give you the 0 vector out. In other words, the Y vector is non-zero. We're trying to show positive definiteness. We're going to deal with this non-zero vector, Y, as opposed to the original one in some of the manipulations. Okay, C was hypothesized to be positive definite. That means this. Means if we take a non-zero vector, transpose it, matrix C times vector, we get something that's positive. Okay, and that's where we're using the Y vector. All right, so we want to take, we're ultimately trying to show A transpose CA is positive definite. So we'll take A transpose CA, multiply on the left and the right by an arbitrary non-zero vector. That's what vector X was, of appropriate dimensions. Okay, let's toy with this transpose and write X transpose times A transpose is AX transpose, properties of transposes. Now we've got an AX transpose times matrix C times AX. These are vectors. In fact, we define that to be vector Y. So this becomes Y transpose CY. What do you know about matrix C? It was given to be positive definite. Okay, then this expression must be positive. So what we've shown is that A transpose CA is positive definite. Well, we still need to show some symmetry stuff. Positive definite satisfy this kind of condition, and the matrix was symmetric. So we need to establish that, but that's a piece of cake. So we've taken this matrix, multiplied on the right by vector X, column vector X, on the left by X transpose, row vector, and shown that we get out a quantity that's positive. So that's the positive of positive definite, I suppose. We still need to establish the symmetry. Easy. A transpose CA, transpose the whole thing, property of transposes, transpose each constituent and write them down in the reverse order. So we get A transpose first, C transpose in the middle, A transpose transpose at the end. That's A transpose. Remember, C was positive definite, so it was symmetric by definition. So C transpose equals C, and A transpose transpose is A. There you go. We transpose this matrix. We got the matrix back, so it's symmetric as well. So A transpose C times matrix A is positive definite. It's symmetric and it satisfies this kind of condition. This kind of condition here. Multiply it on the left and the right and get the non-negativity. Okay, positivity, excuse me. Next, converse of that, if A transpose CA is positive definite, then A is a full column rank, M, whatever. Well, suppose not, okay? Full column rank means, well, it means the columns are linearly independent. Well, suppose not. So we're going for proof by contradiction. Assume that A is not a full column rank, then the columns of A are not linearly independent. So there's a dependence relation on the columns. Let those columns be denoted, as we've often done, by A1 through A sub m. All right, there's a dependence relation, where we stand now, on these column vectors. So let's take scalars, x1 through x sub m, not all of which are 0, such that linear combination x1a1 plus x2a2 up through x sub m a sub m equals a 0 vector, not all coefficients 0. In other words, A is not full column rank, then its columns are linearly dependent and there exists a dependence relation. Okay, so let's concentrate on this vector x of coefficients. It's not the 0 vector, right? Right, not all the coefficient, I'm sorry, not all the not all the components of vector x were 0, because not all of these coefficients, which are equal to the x sub i's, are 0. So we don't have a 0 vector, yet we still have ax equals 0. Well, that's how we got here. We took matrix A times vector x, produced this linear combination, and got out the 0 vector. So we've got a non-zero vector to which we multiply A and get a 0 vector out. All right, we've assumed A is not of full column rank, and we are working under the operation that A transpose CA is positive definite. Okay, so this matrix A is going to cause some, this vector X is going to cause some problems. Okay, so let's take A transpose CA, multiply on the right by X, the left by X transpose, and let's associate some things, isolating the A and the X. Haven't changed anything here. Hey, A times X, we know that to be 0. That's how we chose the X vector. I told you it's going to cause trouble. So we get a 0 vector here, and it is a vector, it's a column vector. But we've got a matrix times this 0 matrix, if you like. Of course, that's going to give 0 out. So we took a non-zero vector X, and we did this kind of manipulation with respect to this matrix. We're supposed to get something out greater than 0 because that matrix is positive definite. We didn't. We got 0 itself out. So A transpose CA is not positive definite. That won't happen with a positive definite matrix. That contradicts our hypotheses of positive definite. So the assumption that A is not full column rank is false, and A is indeed a full column rank. Back to the notes. Okay, we're going to look at some properties of products of this sort. So we're going to take a matrix A, transpose it, and multiply it by A. If A is an n by m matrix, then indeed A transpose A is defined. So is A times A transpose. But the dimensions work out, so we do the transposing, the product exists, and we're going to make a bunch of claims about this product A transpose A. This is called the Gramian matrix of matrix A, a term new to me, I have to admit. But the claims are A transpose times A is a 0 matrix if and only if A is a 0 matrix. A transpose A is non-negative definite. So we do that X transpose X thing, we'll get out something that's greater than or equal to 0, non-negative definite. A transpose A is positive definite if and only if A is a full column rank, similar to what we had above. We didn't have exactly this in what we stated previously though. A transpose A times matrix B equals A transpose A times matrix C if and only if AB equals AC. So some multiplication by B and C on the right. We get a similar type result by multiplying by B and C on the left, and a similar type conclusion, except this one has transposes in it. The A's are on the other side in this one as well. We multiplied on the other side. A transpose A is a full rank if and only if A is a full column rank. And this is a clean one here. The rank of A transpose A equals the rank of A. So a bunch of claims. Let me keep this in the background. We'll have to jump back and we'll go through the proof of all of these. We'll have to jump back to the statements occasionally. Okay. Part one. A transpose A equals 0 if and only if A is a zero matrix. Well, if A is a zero matrix, so is A transpose. The product is a zero matrix. How about the other half? Suppose A transpose A equals the zero matrix. Then the trace of A transpose A is 0. Sum of the diagonal entries. By the way, A transpose A is a square matrix. It's M by M, isn't it? Yeah, it's M by M with the dimensions we were given. It's a square matrix. So let's find the ij entry of A transpose times A using my little notation that I introduced. How do you multiply matrices? Well, you get the ij entry. You take sub ik of the first one and sub kj of the second one, sum over the appropriate k's. Here, first matrix is a transpose of matrix A. So short term, I'll denote that A sub ik with a superscript of t to indicate it's the entry in the transpose of matrix A. Second, A sub kj. That's the way we take matrix products by definition. Let's transfer this from a conversation about these elements of the transpose to elements of matrix A itself. So A sub ik super t is the same as A sub ki. Swap the indices. My little t really means just transpose the indices. Okay, so here's what we get for the ij entry of the product. Remember this thing about the trace? Let's find the ii entries. Then we'll find the trace. We know that's 0, and that's how we'll draw our conclusion. Okay, you want the ii entry? We'll set j equal to I up here. And then we'll get the ii entry as a sum from k equals 1 to n of A sub ki, A sub ki. So we get A sub ki squared. There's what you get along the diagonal of A transpose A. And remember, that sums to 0. Oh, well, duh, if it sums to 0, all these things are squares. All these things must be 0. And that's how we'll ultimately get the conclusion. Some more details. We know 0 is the trace of that product. We know the trace is the sum of the diagonal entries. Okay, those diagonal entries are of this form. We've got an m by m matrix, so we'll sum from I equals 1 to m of the ii entry of that product. Okay, so that's given by this, as we argued upstairs. See, we can rewrite that in terms of, all we did was change variables here from k's to j's to get this. We can interchange, let's see, we interchange the i's and the j's to get this. I mean, ultimately, I want to say, you see all the ij's are there. So this is some fiddling around with indices, dummy variables on the indices. And that's where it happened. We've got 0 equals the sum of these squares. I ranges from 1 to n, j ranges from 1 to m, A sub ij. That's all the entries. That's all of the entries on that range of i's and j's from that matrix product. A sub ij squared must be 0 because when you sum them up, you get 0. And that must hold for all I and all j. In other words, next slide, all the A sub ij's are 0. And so matrix A is 0. And that was the claim. Okay, like I said, let's pop back and look at the statement. So we've got the first one done. Second claim is A transpose A is non-negative definite. All right. Take yourself Y, a vector from Rm, and let's consider Y transpose. We're trying to show A transpose A was non-negative definite. Take Y transpose, A transpose A times Y, the matrix with a Y on one side and transpose Y on the other. We can rewrite that, associating Y transpose and A transpose. Properties of transpose, we can write that as AY transpose. Okay, we got an AY transpose on the left, we got an AY on the right. Remember, we're thinking of Y as a column vector, so AY is a column vector, so AY transpose is a row vector. So when you do this type of matrix product, you're really just getting the inner product of AY with itself, dot product if you like. You're getting the norm squared of that vector. Oh, and the norm squared of a vector is greater than or equal to 0. So there you go. Arbitrary vector in what we get out is greater than or equal to 0. That's non-negative definite. Okay, so non-negative definite is easier than positive definite. Speaking of, part 3, as you deal with positive definite. So A transpose A, the Gramian matrix associated with matrix A, is positive definite if and only if A is a full column rank. Column rank. Okay, some of these arguments through these proofs are rather similar. All right, we just saw that if we take any vector, we're not going to want to use a 0 vector if we're trying to show positive definite. Up here, we didn't care. We were showing non-negative definite up here. But from part 2, we saw Y transpose, A transpose A times Y, is the norm squared of the vector AY. So the only way we're going to get 0 out is if AY equals 0. As before, AY is a linear combination of the columns of matrix A. So if A is of full column rank, then the columns are linearly independent. The only way you're going to get out AY equals 0 is if Y equals 0. So we get AY equals 0 if and only if Y equals 0. This is the same argument we just had, only we left some of the details out, where we set up a dependence relation. We've got linear independence in this case because we've got full column rank. So you set up a linear combination set equal to 0. There is no dependence relationship. We would have to have all the coefficients be 0. In other words, matrix Y has to be 0. Okay. So if A is a full column rank, then if Y is not the 0 vector, then we're not getting AY to be the 0 vector. So whatever vector it is, it's got positive norm or positive norm squared. And A transpose A is positive definite. Of course, A transpose A is symmetric. Let me peek at the question again. So we've shown positive, let's see, it was an if and only if, wasn't it? We've shown if the columns, here it is, if the columns of A, if A is a full column rank, if A is a full column rank, then A transpose A is positive definite. Okay, I think it was an if and only if result. Yeah, so we've shown if A is a full column rank, then A transpose A is positive definite. Now we want to show the other implication. If A transpose A is positive definite, then A is a full column rank. Let's consider the contrapositive. So what we'll actually show is if A is not a full column rank, that will allow us to get a dependence relationship. Then A transpose A is not positive definite. And this is quite similar to what we just did. Oops. Okay, if A is not a full column rank, then the columns of A are not linearly independent. Call those columns A1 through A sub n. We can find scalars Y1 through Y sub n, not all of which are 0, such that the linear combination equals 0. All right, so there's a matrix Y with these as its components. It's not the 0 vector because not all its components are 0. And A applied to that matrix is 0. Same argument as we had upstairs. Now if we'll apply A transpose A, multiply it on the right by Y, the left by Y transpose, you know you're going to get the norm squared of AY that was demonstrated up here. That's going to be 0 because AY is a 0 vector. Well, that's not positive definite. So we needed, whenever we chose a non-zero vector Y, that we got this to be greater than 0. It equals 0. We don't have positive definite. So there's an argument for the contrapositive. So in part 3, we've got positive definite see where I want to point. A transpose A is positive definite if and only if A is of full column rank. So that's what's been shown. Next, part 4. Okay, so let's see. We want to take the Gramian product, multiply on the right by 2 matrices, and show we get this relationship here. Multiply on the left by 2 matrices, and show we get this relationship here. Okay. Suppose we've multiplied on the right, and we get that equality. Then we can rearrange, subtract, to get A transpose AB minus A transpose AC equals 0. Just took this to the other side with some subtraction. We can factor the Gramian product, A transpose A, factor that out. We're left with a B minus C. Okay, we got equals 0 from the arithmetic we've done. Let's multiply both sides of this equation on the left by B transpose minus C transpose. Can't argue with the validity of it. Is there any motivation to this? Yeah, I want to get those transposes together. You know where we're going with that kind of manipulation. So let's multiply by B transpose minus C transpose. Okay, on the left-hand side, you pick this up. On the right-hand side, well, you're multiplying by a 0 matrix. So you still got a 0 matrix on that side. Then we can take this product of transposes and rewrite it as a transpose of a product that reverses the order. And if you like, removes the transposes on the constituent parts. Now we've got A times B minus C transpose times A times B minus C. That must equal the 0 vector. In part 1, we said when I have the transpose of a matrix times a matrix equal to 0, that implies the matrix is a 0 matrix. That was part 1. If the Gramian product is 0, then matrix A is 0. Here's the Gramian product of this matrix with the transpose on the left. So this matrix must be the 0 matrix, part 1. A times B minus C must equal 0. That is, AB must equal AC. Distribute and move things around. So if we have this kind of relationship, then we get AB equal to AC. Conversely, if AB equals AC, then we'll just multiply both sides on the left by A transpose, and we get this relationship. So we do have an if and only if relationship in terms of these types of products. How are you going to do it in the other one? Same thing. Suppose we have B, A transpose A equals C, A transpose A. We'll subtract. Let's go through this a little bit quicker. Factor, multiply on the right by an appropriate transpose, choosing B transpose minus C transpose, again on the right. On the other side of the equation, we get a 0. Okay, we can take this product of matrices and write it in terms of a transpose. That introduce A as an A transpose, goes from the left to the right. The B transpose minus C transpose becomes a B minus C. We got that transpose outside here. Standard transpose manipulations. That equals 0. Hey, part 1 tells you we've got a matrix and its transpose, a Gramian product equal to 0. That implies the matrix must be 0. So B minus C times A transpose must equal 0. Distribute, rearrange, that tells you BA transpose equals CA transpose. That was the conclusion. So if we have this relationship, then we have this relationship. It's kind of like you cancel the A's. You can't do that because what, A doesn't have an inverse. So I don't know that we can eliminate that. That's why we go through this particular argument. Conversely, it's easy. If you got BA transpose equals CA transpose, multiply both of them on the right by A, and we get this if and only this. That was the claim in part 4. So repetitive arguments, really. Let's take a look at part Part 5, A transpose A is of full rank if and only if A is of full column rank. Okay. Suppose A is a full column rank, denote it with M, has to be less than or equal to the number of rows. Then we know Theorem 3.3.12, the rank of A transpose A equals the rank of A. That's a second result we just did. Rank of A we've denoted with the symbol M. All right, so we got that relationship. A transpose A is M by M, so A transpose A is a full rank. So it turned out that was fairly easy. If A is a full column rank, then A transpose A is of rank M, and given the dimensions, that's full rank as well. All right, now suppose, I said if and only if, suppose A transpose A is a full rank M. Okay, getting a lot of mileage out of Theorem 3.3.5. By that theorem, the rank of A transpose A, denoting as M, is less than or equal to the minimum of the rank of A transpose and the rank of A. Okay, that's less than or equal to the rank of A. It's also less than or equal to the rank of A transpose, but this is the one I want to talk about. Okay, so M, the parameter determined up here, is related to matrix A, and that A is N by M. So we've shown the rank of A, M is less than or equal to the rank of A. All right. Well, if A has M columns, then the number of columns equals the rank of A or more. There's not room for more pivots if you think of it in that sense. So it must be that A is a full column rank. It could be rank less than M given these dimensions. It couldn't be rank bigger than M. The rank can't be larger than the smaller of these two dimensions. So by showing M is less than or equal to the rank of A, you're showing the rank is equal to M. And so we've got full column rank for matrix A. Part 6. Okay, says the rank of A transpose A equals the rank of A. All right, let's see, did we just use that? Look back here. Let's see what we used here. We didn't use that here. Possibly I said I did. We used Theorem 12. What we had done is taken A and multiplied on the left by a full row rank matrix. All right, we've multiplied by a full row or column rank matrix as appropriate. There, we didn't actually assume the rank of A transpose A equals the rank of A. It looks like that's what we've done, but the full rank stuff was playing a role in that one. Here, we're trying to show rank of A transpose times A equals the rank of A. No hypotheses, no full column rank or any of that stuff. All right, it's going to take a while. Let the rank of A be represented by R. If R equals 0, then we're dealing with a zero matrix, and, well, those ranks are the same. So without loss of generality, we can take the rank to be greater than 0. All right. The columns of A can be permuted around so that the first R columns are linearly independent. We've done a bunch of that as of late. That tells us there's a permutation matrix Q, such that if we'll take A, multiply it by Q on the right, that permutes columns around. We can move those columns to the left such that we can create a partition matrix where A1 is a matrix of appropriate size and of rank R. So it's the rank, you've collected together all the linear independent columns in a sense on the left-hand side. You can do that, and you can do that with a permutation matrix, multiplying on the right. Okay. Let's see, Theorem 3.3.3 said the rank of AQ equals the rank of A. That dealt with taking a matrix and multiplying it by a product of elementary matrices, if memory serves. And that doesn't change rank, was the claim there. And that's exactly what we've got here. So we've got the rank of AQ equals the rank of A. It's this parameter R. All right. So let's see what's going to happen next. At some point, and I warned you this is a lengthy one. At some point, we need to talk about A transpose A. Okay. So let's see. A, should read A1, is a full column rank. So we got full column rank on this part. This is part of A. And so every column of A sub 2 then must be a linear combination of the previous columns. We've done this before as well, isolating the linear independent parts of these matrices. So every column in A2 is a linear combination of the columns in A1. So there's a matrix B that will produce that linear combination of the columns of A1 to produce the columns of A2. We've done this before as well. Multiplying on the right by a matrix takes linear combinations of columns here. Then we can take AQ, which is related to A, through the permutation stuff, which we've written as this permutation matrix. We can write that as A1 times an identity matrix. And A2, we just saw we could write as A1 times some mystery matrix B. All right. I got A1 in each of the pieces. We can rewrite that partitioned matrix as A1 times the partition matrix identity and matrix B. So a smaller partition matrix. So if we take AQ transpose, we're going to transpose this. That's equivalent to transposing the A1 times the little partitioned matrix. That will involve reversing the order in the product and transposing the constituent matrices. We'll get A1 transpose on the right. Here we'll transpose. So this partition that runs left and right will become a partition that runs up and down. We'll also have to transpose the constituent parts. Transpose that identity, nothing happens, symmetric. Transpose matrix B. So when we calculate AQ transpose, we get something of this sort. Let's take a product. Let's take AQ transpose times AQ. You like that? I'm desperately looking for A transpose times A times A in some of this stuff. So that's a little bit closer. Okay. Let's see, AQ transpose. We just saw this can be written here like that. AQ was written as this product involving the partition matrices. We're going to define matrix T to be this partition matrix. R by R identity, R by M minus R zero matrix over here, I think it is, negative B transpose, and another identity matrix. Any observations about this matrix T other than why you would want to do this? Excuse me. Let's see, it's lower triangular for one thing. Right, we got these identities running down the diagonal. We've got some zeros below in these two pieces here, some non-zeros below the diagonal apparently as well, but definitely nothing but zeros above the diagonal. So define T to be that matrix. All right. T is M by M. It's a full rank. Yeah, it's a diagonal matrix. It's got ones all along the diagonal. It's a full rank matrix. So if we want the rank of A transpose A, we can say that's the same as the rank of AQ transpose times AQ. All right, why is that? A doesn't equal AQ, right? But they got the same columns. Remember, what we did to produce this AQ matrix was permute the columns of A. So we got the same columns here. And a similar type story then for the transposes, with the same rows, I guess. So that'll give us a situation where we get the ranks to be equal. All right, now Theorem 3.3.12 says if you'll multiply by full rank matrix in there, that doesn't change ranks. So we're sticking this matrix T in right here. Can't argue with the validity of it. motivation I could use some more of. I'm looking for A transpose times A in some of this stuff. But you would have to agree I can introduce that matrix T. We could transpose. So I've introduced a matrix T on the left. Don't want to transpose. I want to introduce a T transpose on the right. If T, a square matrix, is full rank, then T transpose is full rank as well. So first we'll multiply on the left by T. Theorem 3.3.12 lets us do that. Secondly, we'll multiply on the right by T transpose. Full rank matrix, the theorem will let us do that as well and not change ranks. All right, let's call that asterisk. We'll be coming back to pick up asterisk later. For now, I want to look at partition matrices. Trying to get to A transpose A. Okay, let's see. Let's take this thing here. We got T AQ transpose. T AQ transpose. All right. This is what we defined T to be. We had AQ transpose, previous slide, written like this. So let's do some multiplication here. We'll do a row times column thing, row times column, the way you multiply partition matrices. All right, so we got some zeros in there. We'll be left with an identity. We actually get some cancellation down here. That's why the negative must have been put on that B back when. And we get negative B transpose times an identity plus an identity times B transpose. Well, that's appropriate size identities. That's negative B transpose plus B transpose, 0. Matrix of appropriate size. And we got the A1 transpose on the outside. We could put that inside the partition matrix and produce something like this. If we take AQ times T transpose, the second thing inside that matrix product there, we could rewrite that using transpose. We would do that to get the same kind of thing we had up here. We get T AQ transpose, all transposed. So that's the transpose of what we have up here. So that equals the transpose of what we got here. So we'll get this transpose, vertical becomes horizontal when transposing, and we pick up an extra transpose on the A1 to give us that. All right, so we've got, let's see, this rewritten as given here, that rewritten as given here. We had the rank of A transpose A equals the rank of this stuff. So let's take this and substitute that and that in the star equation.